Hello, my name is Chris Smith. I'm co-CEO of Applied Brain Research, or ABR, and a professor at the University of Waterloo. Today, I'm going to be talking to you about some of our tools and new kinds of neural networks for processing language in extremely low power settings. I'll be talking in particular about three main aspects of this focus. One is a tool called NengoEdge, which lets you easily build efficient and very accurate AI and target it for specific hardware, so train it for that hardware. I will also be talking about Legendre memory units, or LMUs, which is a new kind of neural network which has certain optimality properties, which is very rare in neural networks, that we can show make it extremely good for processing time-varying data. And then I'll be talking about TimeSeries processors, or TSPs, our use of the LMU in a hardware context to build ASICs. In all three cases, I'll be using examples from language, speech processing, natural language processing, as a demonstrator application. But much of what I'm going to discuss will apply to any kind of time-varying data. So let me begin with NengoEdge. As many of you know, programming hardware at the edge is actually quite difficult. And this is for several different reasons. One is that there are no general tools, so I can't build a program in a software tool and then have it compile to many different pieces of hardware. And of course, there are many different pieces of hardware. I have a bunch of them listed on the right-hand side here, but this is an ecosystem which is constantly growing as people come up with new improvements to hardware. So if I have the job of trying to program a piece of hardware, I have several challenges ahead of me. One is setting up a development environment, and this can be quite complicated and it can be different for every piece of hardware. As well, it's difficult to compare the options. So if I want to have 4 pieces of hardware that I'd like to see how my algorithm runs on, I have to set up 4 different development environments. I have to train my model for each of those 4 different targets if I want optimal performance, and then I have to gather similar characteristics or statistics off each of those pieces of hardware and compare them. This can be a lot of work and have an enormous amount of engineering overhead. And finally, I often have to change my model depending on the hardware that I'm targeting. If I'm trying to program a TPU or a microcontroller, I might have very different ways I have to set up my network architecture in order to have them run well on that piece of hardware. So this kind of fragmentation is extremely difficult for me as a designer to make good hardware decisions without having an enormous amount of overhead. So what we're trying to do at ABR is decrease the amount of effort it would take to do that kind of cross-hardware comparison. Our new platform called NengoEdge lets you build and test solutions for your problem, and it takes each of the pieces of hardware that you choose to compare, performs optimizations for that particular kind of hardware, and then runs your solution on the hardware and reports the results back to you. Of course, all of this is happening in the cloud, so we're the ones who optimize and maintain the different hardware backends that you'd like to target. Essentially, from your perspective, you bring your data, you pick the hardware you want to compare on, you hit optimize, then you get a bunch of results back, you compile that solution, and then you can deploy it on your hardware locally. So how are we doing this? We're leveraging our decades of experience building a neural development environment called Nengo. Nengo is a full-featured suite of a GUI, core, simulator, and other components, which lets you build extremely large models. The world's largest functional brain model has been built using Nengo. But what it provided for us in the context of hardware is that it was also designed in order to target neuromorphic hardware, as well as standard kinds of hardware such as CPUs and GPUs, which allowed us to become experts at understanding how neural networks are best run on different kinds of hardware. In the context of NengoEdge, this has allowed us to build a system which is both easy to use and effective for solving that hard engineering problem that I discussed before. It lets you go from a raw data set all the way to deployment on a particular piece of hardware. I have a diagram on the right here which outlines the process, and later on I'll show a brief demo video. Let me just summarize by saying you bring your data to NengoEdge. You then pick a particular model definition, choose how you want to train that model, pick a particular kind of hardware, and then hit optimize, and NengoEdge does the rest in the cloud. Once it's finished optimizing, it will run that particular model on the hardware you chose and provide you several metrics about latency, accuracy, power usage, and so on. And then if you so wish, you can test it live, or you can download the artifact and deploy it. Our intent is to provide a tool to make it much easier to make those data-driven decisions, because you can perform exactly the same process across many different pieces of hardware and know exactly what kind of resource demands are required from your final product in order to meet the latency, power, and accuracy requirements that you desire. Now you might think, okay, this sounds great, but how is this different from any of the other kinds of edge offerings out there? Is there something that would make me use NengoEdge instead of another platform? And the short answer is yes. So let me introduce our special sauce. And of course, I gave this away a little bit at the beginning when I mentioned that we have a new kind of neural network called the Legendre Memory Unit. And of course, it's central to NengoEdge. So to give you a sense of what the Legendre Memory Unit, or LMU, does, let me describe what looks like a simple problem to start. This is the problem of delaying information over time. So suppose I have this gold input signal. I have a system sitting in the middle, which takes that input signal and delays it by some amount of time, say 1 second, and generates that blue output signal. So this seems pretty straightforward. All I have to do is take the same thing and stick it out. But in fact, it's an infinitely difficult problem because I haven't put any constraints on that input signal. So it can have extremely high frequencies. Those high frequencies mean that things are changing very rapidly over that 1 second, and I have a lot of data to memorize. So in fact, it turns out if I don't put any constraints on my signal, this is an infinitely difficult problem. However, we can optimally solve the problem of approximating a solution to this problem as well as possible given finite resources. And this is exactly what the Legendre Memory Unit has at its core. So we can prove from first principles that the LMU is the optimal finite solution to this difficult problem. So I'm showing an example here where we have an input as a blue line going into the LMU. The ideal output is a dashed blue line, and the output that the LMU generates is a green line. As you can see, there is hardly any difference. But of course, what's the big deal? Is this useful? Why do I want to just remember something over some length of time if I'm trying to solve difficult AI problems? I think you can get an intuition by realizing that we already know neural networks are extremely good at computing complicated nonlinear functions of their input. But what we haven't been able to do until now is take a temporal sequence, optimally compress it, and then pass it through that neural network, which is extremely good at computing nonlinear functions. So really, this is what the Legendre Memory Unit is doing. So the Legendre Memory Unit, which I've diagrammed on the right-hand side here, consists of two elements. One is solving that optimal compression problem that's marked linear here. And then the other is a nonlinear layer, which is computing some function of that information. Now, one thing I will note is that typically those matrices A and B are the things that we have defined to be optimal. Everything else is trainable, as typical in a neural network. So we're quite excited from a theoretical perspective because this really is a new kind of neural network. It's a structure, it's an architecture, it has a core which people haven't used before. And as I mentioned, we can derive this from first principles, and we know that it has certain optimality properties. But of course, the real question is, how well does it work? So here we're comparing an LMU to that workhorse of AI, especially for recurrent networks processing time-varying data, the LSTM, or long short-term memory. As you can see, especially for long delays, the LMU is far superior to an LSTM, being about 1 million times more accurate while remembering 10,000 times more data. And furthermore, it has about 80 times fewer parameters. Now, in some ways, we shouldn't be surprised by these extreme numbers because this is what the LMU is optimal for. This is a delay test. However, the LSTM is only one of many solutions to dealing with time-varying data. How is the LMU compared to others? In this slide, we have a whole slew of recurrent neural networks processing the same benchmark called permuted sequential MNIST. So you can think of this as like MNIST, but for recurrent networks instead of vision systems. Of course, that means it's simple, but it also means that it's been tested on many different varieties of recurrent network. And as you can see, the Legendre Memory Unit outperforms them all. The LMU in the graph has 97% test accuracy and has 60% fewer parameters than all of the other networks listed there. That makes the LMU state-of-the-art with 60% fewer resources than any other technique. When we allow that LMU to have full parameter count, we push the accuracy even higher. And in fact, we've used the LMU on a wide variety of data sets and shown state-of-the-art across many of them. But today, let me focus on LMU application to language, and let me start with speech. One simple but commercially relevant application of speech processing is keyword spotting. Last summer, Google released a paper comparing a wide variety of state-of-the-art networks on the keyword spotting task. In particular, they were using Speech Commands 2.0, which has become a standard data set for comparing keyword spotters. As you can see here, all of the Google networks were good, so they were scoring above 95% for the most part. However, compared to an LMU, they were quite large. On this graph, we have accuracy on the left-hand side, and the size of the model gets smaller as you go to the right. For the best models from Google, we could build models that matched their accuracy, but were smaller, and we could further decrease the size of those models while beating other keyword spotters people had proposed. So essentially, you get this Pareto optimal front. For any combination of accuracy and model size, the LMU seems to do the best. This lets us claim that the LMU gives the world's most power-efficient streaming keyword spotting models. This was a study done in software, but we took the same techniques and targeted specific pieces of hardware. Here I'm showing examples for an ARM Cortex-M7. We picked the M7 because ARM themselves had used that as an example of keyword spotting. And here we're comparing the accuracy and inference speeds that we got. You can see that we have about a 10x improvement on inference speed, meaning that you're going to have much less power use or you have more cycles for doing other things. And this is using standard commodity edge hardware. And in fact, the accuracy we're displaying here has improved since. So as you can see, NengoEdge has this secret sauce, the LMU, which allows it to build state-of-the-art, better than state-of-the-art models and deploy them to specific pieces of hardware. So to give you a better sense of what the interface looks like, let me show you a brief demo video. When you first sign on, you are greeted with a projects page. And here you can see we have a few extra projects, but likely the first thing you'd want to do is upload a data set. So if we click on data sets, we can see past data sets that we've uploaded, but we can pick a new one. So I've got a little simple KWS data set here that I can upload. Call it my KWS. Upload that. Once the data set is uploaded, it's added to the list of data sets that we can then use for doing our optimization. We can head back to our projects page and we can see we have several projects that are already been set up with other data sets. Some of these are prepped to run, others have run and actually have results ready. In this instance, we'll create a new project. So we'll again call this my KWS project and create it. And the new project that we've created at the bottom here is empty. So we want to start with an initial run. For the run, we can collect or select the hardware that we'd like. We can select the data set that we'd like to use. If we'd like, we can use transfer learning by training from an initial set of weights that were trained on a different data set. We can then specify elements of our architecture, pick different kinds of LMUs. We can specify various parameters about those different layers within each LMU. We can specify training parameters, audio preprocessing parameters, and so on. In this instance, I'll just set up a simple training example, which we aren't really going to use. We can then give it some of the keywords that we'd like it to optimize for. And then we can click optimize here if we want it to kick off the run immediately, or if we go back to our projects page, we'll see that it's prepped to be optimized. We can go back in and edit some of those configuration elements, or we can click optimize. And this will now take all of these settings in the configuration file and begin the optimization for that specific piece of hardware using that data set and that particular LMU model. We won't wait for this. Instead, we can just go and look at some results from previous models where we have a bunch of different parameters and so on that we've played with. Looking at the results from some of these runs, we can see things like confusion matrices across a bunch of different words. We can look at the streaming efficacy, speed, size, and so on. And we are continuously adding to the various metrics that we have in the results page. We can then move to deployment, where we can either deploy locally by downloading the model in various formats, or we can test out our model in the cloud by starting a recording, left. This now adds an audio clip that we can verify, left. And then if we want, we can send it to our model to see if the model can successfully classify this particular example. And that essentially completes a really quick tour of the Nengo Cloud interface. As you can see from the video, we now have a complete pipeline available, and we're interested in onboarding additional alpha users into our testing. If that sounds like it might be something of interest to you, please contact us at sales@appliedbrainresearch.com. Keyword spotting is just the beginning. The neural networks for keyword spotting tend to be quite small, and people are already using NengoEdge for applications other than keyword spotting. But in order to demonstrate that the LMU is going to scale to the largest and most difficult models, let us turn to natural language processing. As many of you know, the largest neural networks out there, like GPT-3, have hundreds of billions of parameters, and they're typically focused on natural language processing. So we thought it would be useful to turn to these large kinds of models to demonstrate that LMUs were useful there as well, because of course, natural language, again, is a time series. What I'm showing on the right here is a new architecture that we've developed with the LMU at its core. We take an input sentence, we put it through an LMU that generates a compressed hidden state. We can then reshape the hidden state and use self-attention, which people have been using in natural language processing for years, even before transformers. Of course, in this instance, we have a slightly different kind of representation that we're performing the attention over, and so we call it implicit self-attention, because the attention is being applied to this compressed representation of the input. And then lastly, we can put that through a feed-forward nonlinearity and stack these in layers in order to develop large-scale models. One really interesting thing about this architecture is that LSTMs generally fell out of favor for NLP precisely because they were difficult to train. They were difficult to train because they were recurrent neural networks. So you might think that the same thing applies for LMUs. However, we have techniques for training the LMU in a feed-forward fashion and then deploying it during inference either in a feed-forward fashion as well or recurrently. And in fact, recurrent applications, those that you might typically find at the edge, are much more computationally and memory efficient. To demonstrate how the LMU scales, we borrowed a technique from OpenAI. In 2020, they published a paper comparing the scaling of transformers to that of LSTMs, showing that transformers have this kind of power law scaling that you can see in the top graph on the right-hand side. Not only does the transformer outscale the LSTM, but you can see in the bottom right-hand corner demonstration that it continues to improve as the number of tokens in the context increases. So you can think of this as the length of input that I'm looking at while I make an inference about what should be coming next. LSTMs, unlike transformers, seem to kind of plateau, meaning that they're not getting any better for longer sequences. Transformers, however, continue to have a downward slope at the end of that graph, suggesting that they will continue to improve. So in at least these two ways, transformers outscale LSTMs, which can largely explain why everybody is using transformers now for doing natural language processing, in addition to the fact that they're easier to train at large scales. One contribution of this paper was that authors were able to derive an equation, L of n comma s, which could predict the loss as a function of both the number of parameters or size of the model and the length of training time, or S, the steps over which it was trained. Using the same dataset, we could compare the scaling of an LMU to the scaling of a transformer. As you can see here, under the same amount of training, the LMU does significantly better. In fact, it seems to be improving over the transformer about as much as the transformer is improving over an LSTM. So of course, this is extremely exciting. However, we can also do a comparison where we look at a similarity in loss. So if we match the loss and see how much training it takes, we notice that the LMU decreases the amount of training required by 10x. Now, this is extremely significant, particularly in cases where we are constantly training the model. This is likely to occur at the edge when we want to have NLP applications which are trained for specific users. We can now turn to compare the LMU and transformer in terms of scaling for memory and compute, both over training and during inference. As you might know, transformers scale as n squared, where n is the sequence length, and of course sequence lengths continue to get longer and longer as we build more sophisticated models. The feed-forward LMU scales as n log n in compute and n in memory, both of which are better than the transformer. And the recurrent version of the LMU scales as ON, or linearly, in compute, and in fact stays constant in memory. And this is precisely because it's a recurrent implementation, meaning it just takes one element of the sequence at a time. An empirical example that demonstrates the differences in these kinds of scaling can be seen in this graph at the bottom, where we're using the same GPU to run both a transformer and LMU architecture. As you can see, the transformer runs out of memory after about 4,000 items in the sequence length, whereas an LMU continues to scale up to 16,000 items. Furthermore, we can see that the length of time taken to process these longer sequences for the LMU scales linearly, whereas the transformer is scaling quadratically, meaning it will leave this graph between about 6,000 and 8,000 items. Now, one of the reasons for these big differences between transformers and LMU in terms of compute and memory is because transformers have global attention, meaning they're looking across the entire sequence at the time that they're trying to make an inference. Interestingly, we can take that kind of global inference, and if we don't mind the extra computational and memory costs, we can include that with the LMU. If we do that, we see even further improvements over the transformer by the LMU. Here in purple, we're showing what happens if you don't mind the computational and memory overhead and include attention with the LMU. This opens up avenues for future research where we decrease the computational cost of that attention, something we're exploring at ABR. So hopefully by this point, I've convinced you that the LMU is an interestingly unique and effective algorithm at processing time series data. From our perspective, to take the greatest advantage of LMUs, we want to put it directly on hardware. What does this look like? In some ways, this is not earth-shattering, but an exercise in good hardware design. So we've designed computational blocks, which compute all of the elements required for an LMU, and then we can place those blocks in a hardware design for any particular application. In fact, most of the innovation in this instance is a method for optimal mapping that we use in order to design LMU-based chips. Let us return to keyword spotting for a moment to look at one such design. Here we've taken the keyword spotter, which I described before as an algorithm, and implemented it in an ASIC. Because we have cycle-accurate power modeling, we can sweep the design space by looking at various combinations of clock frequencies and mappings. As you can see from the graph on the right, This allows us to pick an optimal point of a trade-off between power and area. And I should note that additional constraints such as throughput and latency are also respected by these designs. If we compare this design to what is currently available on the market, we can see between a 16 and 24 times energy efficiency improvement even over current ASICs. I'll also note that this table shows if we implement an LMU on an M4 using the NengoEdge optimizations, we can cut the power in half over standard libraries. But ultimately, this design exercise has shown how much of an improvement you can get using LMUs on time series processing. Down the road, looking ahead, our goal is to take exactly these same observations and scale them up. That is, build a chip which not only does onboard speech processing for full speech, but includes medium to large scale natural language processing models on the same chip. We know, because of efficiencies introduced by the LMU, that this design will cost on the order of a few dollars and essentially allow us to bring what are currently cloud features directly to the edge. At this point, let me turn it over to the other co-CEO, Peter Suma, who's going to wrap things up.
Thank you very much, Chris. The LMU algorithm has been patented worldwide, and our chip has been designed and simulated and power measured in simulation and is achieving state-of-the-art results. We've begun first socket sales. We're expecting the chips to be ready in 2023 for the first run. And the reaction we're getting is extremely positive. The idea of putting full speech and NLP on the device, not requiring a connection, and not using a full CPU or GPU, and being all of that available at the price of what today would cost you for a good keyword spotting chip or a smaller size MCU. This is radical. And this is going to change what device makers can think about when they think about how to achieve competitive interactions on their devices. So think of toys talking full speech, think of cars and phones using less power than they do today, and able to do that and continue that conversation in the disconnected case. So we think there's going to be a lot of opportunity, let alone the privacy factor of having your speech transcribed locally and only the data requests going out after that. These things change what is possible and open up a whole new field of capability for device engagement for the product managers and engineers and device companies. So we're very excited by this development. Backing that, we have our software stack, as Chris has mentioned, with NengoEdge. That's available on a SaaS license. First users are in using it. Kasako reviewed it in a detailed manner and gave us a leader position on it, a pre-release. And it's advanced significantly since then. We'll be out in 2022 for general availability. We also have a flourishing services business, always have. We bootstrapped the company to this point, and that's supported by our large team of engineers, scientists, both on the AI side, neuroscience, hardware, and software. We're uniquely positioned in order to capitalize on the demands of AI, both at the edge and in the cloud, and also for increasing algorithmic functionality over time. So we're led by Dr. Chris Liasmuth and myself on the business side. And Dr. Jonathan Tapson has joined to lead the hardware push. He's done 4 startups and launched many chips into production. The rest of our scientists continue to support the hardware and software innovations necessary to drive the business. There's about 23 of us now, about 13 of which are PhDs and supported by a team of engineers, published hundreds of papers in the field. We're now raising a Series A. So we're coming around to finance the tape out of the chips. Unlike a lot of companies raising a Series A in hardware, the chip's already been designed on the strength of both research done in the university, but also work supported by the bootstrapping of ABR over many years. And so now we have a smaller capital need than most. We're seeking a Series A of $10 million to fund both hardware and software and directly go to tape out. So we wish to expand sales and marketing significantly with those funds. We also have a flourishing and growing software and AI engineering business in auto, defense, healthcare, and energy sectors, and achieving $2 million of revenue, and expected to be $3 million plus at the very least coming into this year. So that's it for ABR. We are actively looking for a lead investor for the round. We actually are just opening the round next week. So if any of you are interested, please contact us. Or if any customers are in the audience that would like to enable full speech and language at the edge for prices that before could buy you only keyword spotting, please give us a call. Thank you very much.